want to welcome you to my lecture today. I think I get code, but if you're not um hearing me clearly, please make sure you ask question, okay? So today we actually starting chapter 8, and of course the main topic is estimation. So on estimation today, uh, the focus is going to be on bias and mean-square error. So I needed to pay attention because we're going to have another statistical story today. Okay, so in the outline, I'm going to introduce you to the concept of estimation, the bias and mean-square error. We're going to discuss that as well. Then we're going to also look at what is the meaning of bias and variance trade-off. Then there's going to be examples. Okay, so I'm going to walk you through. Let's start with the estimation. This is a situation. We live in a world where we're actually seeking for knowledge. We want to secure our environment. We want to understand our political environment. We want to understand our medical environment. We want to understand our economic environment. We want to understand everything about our environment. Of course, we need information to be able to do that. Now, the information we're seeking for may actually be is something that we call parameter. And this parameter of interest may be mean, variance, standard deviation, proportion, and so on like that. They are all population characteristic value, and there is no way we can get them, we can get the value determined exactly. The only way we can get the value of the parameter determined exactly is when we got resources to study every element in the population of interest. We are limited by budget, and because of that, we normally end up taking sample. Now, when we take a random sample, then attempt will be made to estimate the parameter of interest from the sample. And that is the reason why you see we're into estimation. Estimation is not about getting the exact value of parameter. Estimation is a way of getting an approximate value of parameter. Don't forget, we're not using all the elements in the target population. And that was why I started here. I said, most of the time, we're interested in estimating unknown parameter related to the population or underlying certain probabilistic model. Of course, it could be average income of a particular population, which is going to be denoted as mu if you're talking about average. It could be a standard deviation of income, which is sigma, numbers of earthquakes in a particular region. And I also wanted to take note that since these parameters, they are numerical characteristics of population, then the population that this will come from, we have an underlying probability distribution. And that was why here, you can see the y1 up to yn could follow normal distribution. Okay, it could follow uniform. It could follow whatever probability distribution. All what we just know is the variable of interest will follow a particular probability distribution that we need to be able to understand before we start choosing random sample from such population. I'm going to say that again. If we want to choose your random sample of data from a population, you need to first understand what is the probability distribution of that population. Okay, that's what I mean. Now, we actually want to estimate the parameter of interest. The idea of estimation is coming from the fact that we're using sample. Don't forget, sample is a subset of the population that you choose randomly. And since you are not using all the items in the population, you will be estimating. Now we got two types of estimation. We got a point estimate, an interval estimate. But let me first say this. There is a difference between estimation, estimate, and estimator. Let me first make a distinction between all of that. I'm going to say that again. Estimation, estimate, estimator. What do I mean by that? Estimation is a process of trying to obtain the values of a parameter using sample information. I'm going to say that again. Estimation is a process of you trying to figure out the value of a parameter given sample information. That's what we call estimation. Estimator now is a particular method or formula that we use in estimation process. A particular method or formula you use. Maybe I want to figure out the mean. Of course, I'm going to use a formula for the mean. The formula that I use in figuring out the mean is an estimator. The process of doing that is an estimation. The result that I got at the end of the day, the value that I got at the end of the day is an estimate. Does that make sense? The value, maybe I calculate the mean and I got a result of 5. 5 is an estimate. But you know what? If I get a single value, we call it point estimate. If I get a value in an interval where I indicated the lower bound and the upper bound, and I said, using a certain level of confidence, and I said the true value of the parameter lies in the interval, then I have interval estimates. In statistical analysis, we got two types of estimates, point and interval. We go from point estimate to interval estimate because of the fact that the point estimate could be wrong or right. According to the classical approach in probability, the probability that a point estimate could be wrong or right is the same, even though you've done all what you're supposed to do. I'm going to say that again. The probability that a single value you got could be wrong or right is the same. Therefore, to be at the safer, side in research, we normally consider interval estimate. We don't want a situation where we've committed a lot of resources only for the value that you got to be wrong at the end of the day. And that is the reason why we don't want a situation, want to prevent that kind of ugly situation, and why we get our results in an interval where we're able to incorporate the margin of error. Okay, so that's what I presented to you here. And that's why you can see a value could be estimated to be around 352. And why the interval is just going to say is within 340 to 363. There's a lot of advantages that come when it comes to interval estimates. Now, I think I've defined estimator the other time. So it's a formula or method, okay, that you use to calculate the value of an estimate, probably based on the measurement that is contained in your sample. Now, if I want to estimate the population mean, maybe I want to estimate the average annual household income in the United States or in a particular country. Of course, we actually our mind is going to go into what I call a measures of central tendency. The measure of central tendency, we have mean, median, mode. But most of the time, or some of the time, we normally use mean. In this class, you're still going to learn which one is better to use out of mean, median, and mode. But right now, I want to first start with the sample mean because it's a commonly used estimator for population mean. Okay? Now, and that was why I said in principle, any statistic can serve as an estimator. Let me tell you this. Like I said, there is not only sample mean that can be used in this situation. We could have more than one estimator. Okay? It's just like an engineer, maybe 10 engineers that work in a particular construction company. They were given assignment to come out with a cost of construction. I know they're basically going to come out with different results, different value. How are we going to know which of these engineers is correct? And that is the same way we're also going to investigate which of the estimator is right. Let me tell you, why are we going to focus more on the estimator and not on the estimate? I'm going to say that again. Why do we need to focus more on the estimator and not on the estimate? Of course, the moment the estimator is wrong, the estimate will be wrong. The estimate is from estimator. Don't forget, estimator is a formula. The moment your formula is wrong, whatever that come out from the formula is going to be wrong. And that is why we focus on the method that leads to result instead of first focusing on the results. Does that make sense to everyone? Okay. Now, and I said, however, some work better than others. In the chapter, we learn about what makes a good estimator. We could have more than one estimator. So how do I know a particular estimator is better than another one? And that will now lead us to something that we call bias and the mean-square error of point estimation. Right now, we only want to focus on point estimation. Don't forget, we got two types of estimation, right? The point and interval. But right now, we only want to focus on the point. Let's take a look at this example. I told you the other time, population parameter They are actually unknown constants. And I need you to pay attention to notation. At times we use theta. You see theta, right? Which could be mean, standard deviation, proportion, and so on like that. Now, when we want to use point estimator, that is a formula or method, we're actually going to put a cap on them. Theta cap is an estimator of theta. Mu cap is an estimator of mu. Sigma cap is an estimator of sigma. P cap is an estimator of P. Please make sure you know the difference between when they got a cap that we also call hats or not. Any question so far? Okay, you're all hearing me clearly, right? You're hearing me clearly. Is anybody struggling with the way I talk? You're fine, right? Okay. Please, if the moment you realize you get stuck or you don't hear me, you pay for the service. You deserve to ask me question. Now, I want to go into an example now. Okay, take a look at this example. We want to sample 100 observations randomly from a population distribution. We already know the distribution. I told you before working on a population of interest, you need to be able to understand what is the distribution, what is the probability distribution. It's just like a lawyer want to maybe take on a particular case. The lawyer need to first ask which states. Okay, I want to believe, going by my knowledge of the legal system in the United States, I remember a case in Georgia about election interference or whatever. If those that are accused, I want to believe their lawyer has to come from that particular state. My knowledge, they may not be able to bring lawyer from outside the state. So, which means if I happen to be a lawyer and somebody decides to hire me from California and I'm in Minnesota, probably there's something I need to do. So, because I need to first understand the territorial jurisdiction where the court that will entertain the case. Very important. So the same thing in statistics. You need to be able to understand the underlying distribution of the population you want to choose from. Right now, the distribution is exponential. Every probability distribution has parameter. I'm going to say that again. Every probability distribution has parameters that need to be estimated. And some of them, they are unknown. Right now, looking at the exponential distribution, the parameter is beta. Of course, theoretically, we know the expected value of y is going to be beta. The variance of y is going to be beta squared. We all know the mean and variance of random variable that follows this distribution depends on the values of beta, which means there's nothing, absolutely nothing I can do without knowing the value of the beta. Because the mean depends on beta. The variance also depends on beta. Okay, suppose beta is unknown and need to be estimated. Oh, before we can conduct any statistical inference using exponential distribution, we need to be able to know the values of beta, but we don't know the values of beta right now. Then we're actually going to consider some candidate estimators, some potential estimators that can be used to figure out the values of beta. We want to be able to see theoretically which of this estimator is going to be the best one. Now, because of that, we actually proposing this. We come up with these three possible estimator. We always are going to have some possible estimators in mind. The very first one is, you can see the cap on each of the proposed estimator. They have a cap on them because they are estimator. They're going to serve as a formula. Like I said, the very first one is Y1. The very first one is just, okay, you know what? Take the first observation. Assuming, we're assuming the values of the beta to be the value of the first observation chosen from the distribution. The second one is trying to talk about taking the mean, the sample mean. And the third one is trying to talk about the products of all the observation raised to the power of 1 over the number of observation. I think the beta 3 is looking to me as a geometric mean. I don't know whether in mathematics you've heard about different types of means: arithmetic mean, geometric mean, harmonic mean. Has anybody heard about that before in mathematics? Has anybody heard about different types of means? We have arithmetic mean, we got geometric mean. The arithmetic mean is when I added all the observation and divide by the number of observation. That is what is popular. Another type of mean is when I multiply them. If there are two values, if there are two observations, I multiply them, I take the square roots. If there are three observations, I multiply them and I raise the power to 1 over 3. Right now, you have 100 observations, multiply y1, y2 up to y100, okay? Then take the root, 1 over 10 root of that. Take a look at that. These are possible estimator. If I really want to know which of this estimator is going to do a great job, the only way to tell is to go by simulation. The simulation is when you are working with artificially fabricated data that I'm actually going to call fake data. And this is what I'm going to do. I'm going to pretend, okay? I'm going to assume a value for beta. When I assume a value for beta, why do you think I'm assuming a value for beta here? I'm assuming a value for beta because I want to simulate from the exponential distribution with that value of beta. Because if I want to simulate from a particular probability distribution, I need to specify a known values for the parameter just for me to be able to, artificially fabricate a set of data that I want to use. You know what I'm going to do? Now I know the values of the beta, right? That I simulated from. And I want to test the performance of the 3 estimator. I want to be able to see the one that will converge, the one that will actually give me what I want. I know what I want. Now, of course, what we're going to do, if we want to try this, we can try this at different sample sizes. And we're going to do that with repetition. You remember what we did the other time, right? With repetition, 1,000 or 10,000, so that we're actually going to have, Y1 in 10,000 times, Y bar in 10,000 times, and the other one in 10,000 times, and we can actually construct the histogram. We construct the histogram, okay? Now, when we construct the histogram, we will be able to see the one that can actually give us what we have in mind. The first one is beta 3. Sorry that is not oh sorry, the first one is beta 2. The second one is beta 3. Okay? And the third one is actually beta 1. Take a look at all of that. If you take a look at the second one, right? Look at the second one. I think the center actually fall at the center of the curve, right? The second one. I'm talking about beta 3, right? If you take a look at the beta 3 here, the geometrical one, okay? So, and when you take a look at the beta 2, okay? When you take a look at the beta 2, you actually skewness, right? And when you take a look at the last one, you can see this guy here, this vertical line, the vertical line, the vertical line correspond to the values of the true value of the parameter that we actually assume before we simulate. Does that make sense? Okay. I'm still coming to all of that. You know, we are because if what you are seeing now, okay, we actually I'm going to explain in detail to you when um we could have some estimator, they could be biased or not. Okay, when they are biased, I'll tell you the meaning. When they are unbiased, I'm going to tell you the meaning. You may not be able to understand what this guy means now because I've not really walked you through what makes an estimator to be biased and what make an estimator to be unbiased. But before that, let me quickly go into this so that you'll be able to understand what I mean. Now, bias and variance. What do I mean by bias? Okay, and what do I mean by variance? I need you to pay attention now. Okay, now I want to start with bias. Situation where the expectation of the estimator, okay, is the same as the true values of the parameter. That is what we call the unbiased. What do I mean? If theta cap is sample mean, I'm going to say that again. If theta cap is sample mean, when I go into simulation, right? Maybe I repeat that 10,000 times. I'm actually going to have 10,000 means, right? The average of the averages, the moment it gives me the true values of the parameter, then it means that estimator is unbiased. The enemy of everyone in scientific community is biasedness. We normally want to try and minimize or remove bias because bias is not good. But let me tell you this. Most of the time, when we make an attempt to remove bias or to minimize bias, we normally create a new problem, which I'm going to call problem of variance. What do I mean by variance? The variance, when you want to conduct statistical analysis, we normally split our data set into two. We got a training set and a testing set. Okay. When your model perform greatly on the training and does not perform great on the test, okay, the reason why that happened? The reason why that happened, you've actually you try to minimize the bias, and in the end, you created a problem of high variance. Okay, when you have low bias, your model will automatically has a problem of high variance. If your model has a problem with high variance, your model will overfit. That's what we call overfitness. Overfitness is as a result of you trying to make sure you have low bias, but in a way, creating another problem of high variance. The high variance is going to be you have so many variables in your model, because the only way you can reduce bias is to increase the numbers of features, the numbers of variables in your model. When you got a lot of variables in your model in an attempt to reduce bias, you're going to create a problem of high variance. What do we mean by variance? The variance is more or less, the sensitivity. Okay, how does your model react, or how does your model the sensitivity of your model to when you to change in training data in training sets, when you change your training set and your model reacts differently, more differently, that means more variance. So, and that is the reason here I'm trying to show you a picture. We can never do without having bias and variance. Bias cannot be completely eliminated, and variance cannot be completely eliminated. Then which one can we tolerate? The one we can tolerate is this guy here, the one I marked here. Okay? Small bias, small variance. That's an ideal situation. That may not be possible. And that is the reason why we need to have a trade-off. Okay? A situation where we can prevent, when you try to reduce your bias, you're going to create a problem of high variance that will lead to overfitting. When you try to reduce your variance, you're actually going to have high bias that will lead to underfitting. Underfitting and overfitting is a problem. How do we actually balance situation? Then we need to have a bias and variance trade-off. Now, if you take a look at this, it's like you want to eat something, you're shooting, right? And you are targeting the blue spots, right? If you take a look at this, very close to that blue spot, and you're actually going to see there's a little variation. That's why you have little bias, okay? You have little bias and little variance. But take a look at this guy. You have a small bias, large variance. That is when you are trying to use a complicated model for simple situation. Complicated model for simple situation. Your model will actually capture noise in the process. Your model will perform greatly on the training data set, but will perform poorly on the test data. That's not good. Now, when you take a look at the next one, take a look at this. You can see all these guys, even though the variance is small, they are very close, right? They are clustered, but they are far away from the target. Far away from the target actually means there's a large bias. When there is a large bias and small variance, it means you are using a simple model for complicated situation. Simple model for complicated. Maybe you are using a simple linear regression model on something that should be non-linear. You are using a simple linear model on something that should be non-linear. Then your model will underfit in that situation. Now, when we balance the situation, when we know we live in a world of sacrifice. You cannot eat your cake and have it. We have to look for a way to balance out between the bias and the variance. Because of that, I'm actually going to move. Of course, I've given you the definition. When the expected value, excuse me, when the expected value of theta cap equal to theta, that is unbiased. When it is not, that is biased. But let me tell you this. It is not all bias estimators that are bad. We got situation where bias estimator is even more preferable than unbiased. Even though the one we're looking for is the unbiased, right? Unbiased. But at times, we may not, practically speaking, we may not be able to get the unbiased estimator of some, distributions. And we're only going to settle with the biased one. But if I want to measure, okay, the performance of unbiased estimator, okay, let's say I have so many unbiased estimator. Maybe I got 3 estimator and they are all unbiased. How am I going to choose the best among the unbiased estimator? I'm going to compare their variances. The one with the low variance is going to be the best. It's going to be the one that is more efficient. What about if I want to compare which one is better among the bias estimator? Among the bias estimator, what am I going to use? Then I'm going to use mean square error. Mean square error. Okay, I'm going to use mean square error. Okay, the mean square error, let me tell you the difference between variance and mean square error. With the variance, if you're talking about the average of square of deviation of observation from the mean, that is the variance. I'm going to say that again. Average of the square of observation from its mean, that is what we call variance. But what do we call mean square error? The average of the square of prediction from the true value. There's a difference between observation from the mean and the prediction from the true value. The variance has to do with the square of the average square of the of the deviation of the observation from the mean. That is the variance. But if we are talking about prediction from the true value, we talk about mean square error. There's something I wanted to see. If you take a look at the first one here, this is a situation for unbiased. You know why? What do you see at the center? What we're trying to say, the expected, when you look at the whole horizontal line, we have so many values for theta cap, so many values for estimator. We plotted that, and the center is this, theta. So this guy is trying to tell me expected value of theta cap equal to theta, which is unbiased. That is what this guy is trying to tell me. But take a look at figure 8.2. So let's look at figure 8.2. Oh my God. The figure 8.2, okay, is trying to tell me a different story. This is a sampling distribution for a positively biased estimator. It's positively biased estimator because the expectation of theta cap is greater. Look at the theta here. Look at the true value here. Look at the expectation here. Which one is greater? The expectation of theta cap is greater. In this situation, it means the expected value of theta cap, right, is greater than theta. In that situation, figure 8.2 is talking about bias estimator. Does that make sense? But when you take a look at figure 8.1, that's unbiased. Because in that one, the expected value of theta cap equal to theta. Any question about these two figures? Now I'm going to move to another figure. Now this time around, I want to compare two estimators. In case you are doing your simulation, if you want to use a graphical analysis, okay, the sampling distributions of two estimators that are unbiased, what makes them to be unbiased? The center is theta. The center here is theta. How am I going to choose? Okay, let me tell you this. I did not include this in your lecture notes, but I'm going to update that because that was what I was doing when I came into this class today. I realized that I should include this. I will update that and include that in the notes, okay? You can check the model. Take a look at these two. We got two unbiased estimator, and we realize that the second one is better in terms of the variance. The variance of the second one is going to be lower than the variance of the first one. And that was why I said estimator with a large variation is this guy. Large variation. Why this one is the estimator with a small variation. In other words, the theta cap 2 is more efficient estimator compared to theta cap 1 because it has a variance lower than the theta cap 1. Any question? Okay. I want to revisit this guy again, where we investigate theoretically. Okay, we're back at the exponential. Okay, we realize if you go back by the law, don't forget the beta cap 1 is y1, right? Expected value of y is the expected value of y1 and it's going to be beta. That is unbiased. Expected value of, and don't forget the beta cap 2 was a sample mean. If the expected value of y equal to the parameter, the expected value of y bar is also going to be equal to the parameter, which means the beta cap 1 and the beta cap 2, they are unbiased. But when you take a look at the theta cap 3, the one that I call the geometric one, this can never. Because when you introduce a log, this is not going to give you the exact value of the true value of the parameter. And let me tell you this, and that was why I said beta cap 1 and beta are both unbiased estimate of that, but beta cap 3 is a biased estimate of that. But let me tell you this, the fact that theta cap 3 is a biased estimate of that does not mean it's not going to perform better than the unbiased. But if I want to compare all of them, what I'm going to do, if I want to compare all of them, don't forget, I can compare all of them using the mean square error that I mentioned the other time. But take note of this. Mean square error, which is going to take us to the next slide. The mean square error, on the other hand, I told you the other time, take a look at this. I said the average of the square, okay, the average of the square of prediction from the true value. Okay, look at this. Theta cap, that's actually like a prediction from the true value. And we can prove that, we can prove mean square error to be equal to the variance of theta cap plus the bias plus the square of the bias. Of course, if I want to prove that to you, what I'm going to do is this. I can assume expected value of that theta cap to be C, and coming from here, okay, which is this guy, I can introduce negative C and positive C in between here. Of course, you know that negative C is going to cancel positive C. When I use the law in mathematics, A plus B all squared, that's going to be A squared plus B squared plus 2AB. That is exactly what you are having here. The one with the 2 into that is going to go to 0. Because under the assumption that the expected value of theta cap equal to C. And in the end, I'm actually going to have this guy. Now, let me tell you this. For unbiased estimator, mean square error equal to the variance. I'm going to say that again. Because unbiased estimator has a bias equal to 0. So if I want to compare between unbiased estimator and the biased estimator, I'm going to compare the mean square error of the biased estimator with the variance of the unbiased estimator. Because the variance of the unbiased estimator is going to be equal to its mean square error. Okay, what does that mean? If theta cap is biased, the mean square error will be greater than the variance. Because don't forget here, if the bias is positive, whether positive or negative, that was why we put a square. Okay, it's going to be additive, to the variance. That was why you are trying to say this. Okay, I want to move now. If I don't finish this today, I'm actually going to continue from wherever I stop in the next class. I think I still have like 3 minutes. Let me quickly. Now, take a look at another example. I have a uniform distribution. Parameter here, 0 and theta. And the f of y equal 1 over theta. Of course, you all know from the CDF is going to be that the mean, okay, when you have a plus b over 2, a here is 0, b is theta. That was why you have theta over 2. The variance, b minus a all squared divided by 12. If you remember what you did on a uniform, that is theta squared over 12. Okay, now if you take a look at this, there are two parameters in uniform, but one is known. The lower bound is known, but the upper bound is unknown. And that is what we want to estimate. I'm not going to rush you. I'm going to start from here, this page, on Wednesday. I need you to ask me question now. Is there anyone who need clarification on what we've done today? Is there anyone? Is there anyone who want to ask question? Is there anyone who need clarification? Before I go, you've been introduced to what we call, bias and the unbiased estimator. And of course, relationship between the mean square error and the variance for unbiased estimator. We talk about the variance of that if you want to evaluate how good is an unbiased estimator. For bias estimator, we pay attention to mean square error. I've told you the difference between variance and mean square error. They are not the same. One is talking about the deviation of the observation from the mean, which is the variance. While the other one is talking about deviation of the prediction from the true value, which is the mean square error. Relationship occur between mean square error and the variance, and the mean square error is going to be the variance plus the square of bias. When bias equal to 0, the mean square error becomes the variance, which means for every unbiased estimator, they got the same value for the mean square error and the variance. If you want to compare bias estimator with something else, you cannot use the variance, but you're only going to use the mean square error. See you on Wednesday. Bye for now, everyone.